Is this the right place?
Yeah, he'll be coming in soon, I think. I just had a meeting with him, so.
Ah, okay.
Hey guys.
Hey,
Hello. Okay, I will be back in 1 second.
I was here earlier and there was nobody. I went away, then I came again, nobody. So I thought that I have a wrong address. So I started to look for it. Now, okay, now there are more people, so that's better. And there is even Grigor.
Hello everyone.
Hi.
Hi. Hi Boban. Let's see if I don't know if Bartek will join. I think no. Today is the Polish Independence Day. It's a holiday here.
Oh,
Oh wait, no, it's not Independence Day. What is it today? No, it is not. They have the Constitution Day. Sorry. The Independence Day is in fall. Okay, so now we did integrations. We did. So I want to give the proof of variability today. I mean, it has three main parts, and I mean, second part is a little bit long, but that's actually the one that I've already did when I proved that you cannot have an iteration tree where where there are no branches of length 2. That proof is representative, but we need the other two. So why don't I do the other two, which we didn't do before, and then next time I'll do that other step. Okay, so the first, let's see if Takeiba is here.
Sorry, Grigor, but do you finish the extender genericity iteration?
Yeah, we proved.
You finished the proof?
Okay, let me outline what we did last time.
Yeah, just remind us. So, thanks.
So we had. Oh, but we can talk about some applications if you want, which is probably important. So we showed that if M is countable, or more like its important part is countable, with delta M is countable and is omega 1 plus 1 durable, and say eta less than delta is wooden, and X is a real, then there is an iteration of countable length such that X is generic for the extender algebra of n at j eta. Okay. So let me just remind you the proof. We suppose outline of the proof. Suppose not. So we don't have such an iteration. So we build an iteration T of M that removes bed extenders. And so what was a bed extender? Definition is bed for X over N, some model N, if for some phi in V critical point of E plus 1 of N. Right, so phi has to be a subset of critical point of V or critical point E. X does not satisfy the axiom generated by E and phi. Okay, so this was bed, but then we needed to make sure that we pick bed, I mean minimally bed extenders, and that was because we wanted to keep the iteration normal. So we need to assume, so this is bed, and when we said, we say E is minimally bed if for X over N, if E is bed for X over N, and there is no extender, and there is no extender F in the ultra power such that length of F is equal to the length of E, and F is bed I guess we don't really need this requirement. And if something, if it's bed up to, we could cut it, right? So I guess I want to say, yeah, okay, so yeah, this is what we want. And F is not, and F is bed for, I guess, less than or equal to, right? But less than lift, and f is bed for x over n. So we take up to length of e. There's nothing smaller that you could. There's no extender of smaller length that could witness bedness, and e is Mitchell orders minimal, right? So e is Mitchell minimal plus length of e. So first we minimize the length, and then we pick the smallest Mitchell order one. And the point of this was to make sure that the iteration is normal. So so what do we do now? Let now sigma be the A strategy for M. Let construct T by induction. As follows. So M0 is M, and E0 is minimally bed for X over M0. Right. So suppose I do have, suppose we have defined M psi E psi less than or equal to alpha. Well, not exactly this way, yeah. And E psi less than alpha. And I have to tell you what E alpha is, right? Want to define E alpha. By our assumption, right? Because we assume X is not generic over M alpha for the extended algebra. At what ordinal? At pi 0 alpha eta. Remember, eta was my wooden. I'm iterating to make X generic. Yeah. So X is not generic over M alpha for the extended algebra. There is a bed, minimally bed E alpha for X over M alpha, right? So that's my next extender. The rules of iteration trees, normal rules, completely determine where of E alpha should go, right? So normal iteration rules determine the predecessor of alpha plus 1. I don't have to say go there. It's already, there's only one place you can go. Okay, so assume now, suppose we have M psi E psi less than alpha limit, right? Then let B be the branch of T, which is right. So I have T up to alpha basically. So let B be the branch and set M alpha to be the branch model. Okay. Now the iteration goes omega 1 steps. Iteration lasts omega 1 steps, producing T t, such that its length is omega 1. And here it would have been convenient if I assumed m itself is countable, but you could think of m itself as countable, yeah? So let's go back to m is L above V delta. When you're iterating m, you're really iterating V delta, you're not iterating these ordinals that are on top. So I could have just thought of m as this countable thing, right? I don't have to carry m with me. Okay, now set V to be sigma t, meaning the last branch, right? So now we need omega 1 plus 1 irritability. There are examples of generosity iterations that last omega 1 step, and then you don't have a branch. I might do an example for you, but if you have omega 1 plus 1 irritability, then you can reflect. Then you can show that this branch, that iteration had to stop.
Sorry, I have a question. You said that you could create an iteration tree of length omega 1 so that there is no branch at all. Not that there is no well-founded, just there is no branch. Or that there is no.
Well, if there was a branch, it would be well-founded, yeah.
Okay, so there is no branch. I see.
There's no branch at all.
You're right. Okay, thanks.
It's once we know this, it's not that hard to do. This is generous iterations. Okay, so what did we do next? So I mean, one important thing to keep in mind is that V is a club, right? So we take now another thing is that T is in H omega 2, because let's just assume M is countable, yeah? Because as I said, it's not important. The important part when you're iterating, the important part is that V delta, it's M itself is irrelevant. The rest of M is irrelevant. So we can think of M as countable, which means T is in H omega 2. Okay, so now let sigma from H into H omega 2 be such that the pair is in the range of sigma, right? Let T bar be sigma inverse T, and B bar be sigma inverse E. The thing to keep in mind, kappa, which we're defining to be the critical point of sigma, is really omega 1 of H. Because B is a club, well, because I'm assuming M is countable, right? Since M is countable, T bar is just really T up to kappa, and B bar is B intersection kappa. And then from here, because B is a club, kappa is actually inside B. Okay, so once we know this, then the key lemma is let's see. So let's set so the key lemma is that sigma restricted to M kappa, which is the kappa model of T, yeah, is equal to pi kappa omega 1. So, I mean, we did the proof last time. Essentially, it's a direct limit construction, right? You take something from m kappa, it's obtained as a direct limit of the previous models. You pull it back into one of the earlier stages and apply sigma to that. So, do you want to see this again?
It's okay.
Okay. Yeah. So this is the sort of the one lemma that inner model theory that drives inner model theory. Okay. So from here, then the next thing to notice, the next thing to do is to go to the next model in B, right? So let gamma be the least.
Can you show again what sigma was, or the previous?
Sigma was the whole embedding.
Okay. Okay.
You're just taking an elementary, countable elementary sum and taking the collapse. And it's
Yeah, H. I didn't say that H is countable. H is countable. Yeah. You take countable elementary submodel like Boban said, and you take a class.
Okay.
Let gamma be the least, such that the gamma plus 1 is in B, and T gamma plus 1 is kappa. So this is the first time you come back to kappa in B, yeah? So you have, the picture would look like you have B intersection kappa, then you have your M kappa, then you have M gamma plus 1, and then you have the rest, M omega 1. And the extender used here is E gamma. Now, E gamma may come from some other model, right? Doesn't come from M kappa itself. Okay, so because of normality, right? Because T is normal, extenders used in B don't overlap, yeah? The picture for B looks like this. This is how the extenders are. Where, you know, the bottom is the critical point, the top is the length. So the next extender used in B has bigger critical point than the length of the previous one. They don't overlap means something like that. Yeah. So this picture never exists on a branch because of normality. Okay, so what that means is that the critical point of E gamma, right, has to be kappa. So that's the next key fact. The critical point of E gamma is kappa. This is because critical point of sigma, kappa is critical point of sigma, which is the sigma is the iteration embedding from kappa to omega 1 from that key claim. But what is that? This iteration is gamma plus 1 omega 1 circle kappa gamma plus 1. And now, because of normality, the critical point of this guy is bigger than the length, right? Because of normality, critical point of pi gamma plus 1 omega 1 is bigger than, or could be equal to, the length of E gamma. Right, so whatever which is bigger than, which is greater than the critical point of E gamma. Right, so whatever the critical point of E gamma is, that should be the critical point of the first embedding here, And so it will stay the critical point. And so from here, it follows that critical point of E gamma must be kappa. Right? If it was smaller, then the critical point of sigma would be smaller. If it was bigger, that means later on you used an extender whose critical point was kappa. But that can't happen because all the further extenders have critical point bigger than length of E gamma.
Sorry, I have one question. Is this extender E gamma, does it belong to your countable elementary submodel? Well, H is the collapse of the countable elementary submodel of H omega 2.
No,
You cannot say that E gamma belongs to.
no. E gamma is further on. Gamma will be bigger than kappa, yeah, or equal.
Yes.
Yeah. So there's
no reason why this extender would be there, right?
Yeah, there's no reason. Well, if gamma equals kappa, then it will be. But if it's bigger, then there is no reason.
Mm-hmm. Okay.
Mm-hmm. Yeah, we don't need it. All we need is that the embedding. All we need is this and then and this, right? Okay, so the other thing, because of what we just discussed, the critical point of, well, I guess I already said it, this fact, but let me record it again. Pi gamma plus 1 omega 1 is bigger than or equal to length of E gamma. Okay, so the picture looks like I get to somehow to n kappa, then I got to, by the way, is my connection good?
Yes.
For me, it is good.
Okay.
There's no problem.
Okay. And then so I have this embedding, which is pi gamma plus 1 omega 1, and I have this embedding. So that the critical point of this one is bigger than the length. And you know, there was m gamma somewhere here that produced E gamma. There may be no connection between these two models. Okay, so let's make some notations to so that the proof is more transparent. Let's lambda by definition is the length of E gamma. Now, why did I use E gamma at stage m gamma? We were using it because it was bad, yeah? Because E gamma is used, E gamma is minimally bad for x over m gamma. Okay, what does that mean? This means there is P in the critical point of E gamma plus 1 of m gamma, such that x does not satisfy the axiom generated by these two guys, but which axiom as computed inside m gamma, right? Now, what is the critical point of E gamma? We discussed that it is kappa, this critical point, right? So, since,
Sorry, why did you say
yeah,
the axiom is computed? What does this mean?
yeah, because I could apply E to some other model and maybe the axiom is satisfied there, but because of agreements, it wouldn't be. So the axiom is the axiom of the extended algebra of m gamma. That's all I'm trying to say, right? So what does X not satisfy? X does not satisfy that disjunction phi if and only if disjunction pi E gamma m gamma, right? So that's the algebra of m gamma phi caret lambda. Lambda was the length of E gamma. This is what X does not satisfy. And that's what I mean by axiom computed in M gamma. Okay, so we have, since critical point of E gamma is kappa, this phi is in V kappa plus 1 of M gamma, which is the same as V kappa plus 1 of M kappa. You may ask why they're the same. It's because we can apply, right? Because kappa is T predecessor of gamma plus 1, the kappa is least, such that exactly this holds. Power set of critical point of E gamma as computed in M kappa is equal to power set of critical point of E gamma as computed in M gamma. And okay, but that's saying now all you have to remember is that critical point of E gamma is kappa, right? This is just the basic fact about iteration trees. When if you're taking an extender from some model and applying it to another model, the power set, the critical point of that extender plus 1 is the same in both models. Okay, so we have this. Another thing we have is that the ultra powers agree, right? So another thing we have is that the ultra power of M kappa by E gamma agrees up to what? Up to lambda plus 1. In fact, much further than with the ultra power of M gamma by E gamma. They agree, they have the same subsets, so they agree, in fact, up to the image of kappa. And the image of kappa is bigger than lambda, because, right? And not only this, but also the embedding as computed in M kappa restricted to the power set of kappa is the same as the embedding as computed in M gamma. This is just a general ultra power fact. If two models agree up to V eta plus 1, and they have an extend, and you have an extender with critical point eta, then these two facts will be true. Okay. All right. So what does this give you? So this tells us that because the axiom, right? Because this axiom was bad, it's the same as computed in M kappa, right? This tells us that A E gamma phi as computed in M gamma is the same axiom as computed in M kappa, right? So what axiom is this? This is the axiom that disjunction phi is equivalent to I-E gamma M kappa applied to phi caret lambda. Lambda was the length of E gamma. Okay, so because the embedding is the same, right? This embedding is the same as the one in M gamma. This is completely true. That's the axiom, right? Okay, so what does this tell you? This tells you that X does not satisfy this axiom, right? So X does not satisfy this. Okay, but it's what it doesn't say. The right to left implication is redundant, right? So it doesn't satisfy this. Okay, and now I want to do one more trivial change. This is the ultra power of m kappa by e gamma, right? So that's just the iteration embedding from m kappa to m gamma plus 1. So that's my, so X does not satisfy P. Well, maybe I should write the longer one and the shorter one. Yeah, that doesn't make sense. Let me write that way. Pi kappa gamma plus 1 P caret lambda implies disjunction of this disjunction phi. Right? So we call lambda is length of E gamma. Kappa is the critical point of E gamma, which is the same as critical point of sigma, which is the same as critical point of pi kappa gamma plus 1. And also pi kappa gamma plus 1 is just pi m kappa e kappa e gamma. Right. Okay, so we have over this model over m kappa. When I take the ultra power by that first extender used in that iteration, that extender violates the axiom. Right? Okay, so what do we do next? Well, we just apply the embedding from m gamma plus 1. Right? Now recall that the critical point of the rest of the iteration from gamma plus 1 to omega 1 is bigger than or equal to lambda. And so when I apply it to this longest disjunction, it's not going to change the first portion of it, right? So this implies that if I apply pi gamma plus 1 omega 1 to the disjunction here, oh, by the way, this should really be, it's better to write it in the other form. And not this. Right? So X satisfies the longer disjunction and it does not satisfy the shorter one. So if I apply the rest of the embedding to this stretch and cut at lambda, I'm just going to get what I had before. Oh, it should be gamma plus 1. Okay, because the rest of the iteration has critical point bigger than lambda. Doesn't change this, doesn't change the sequence up to lambda. And this, the composition of pi gamma plus 1 omega 1 with this one is just the iteration from gamma plus 1 to omega 1, right? So pi gamma plus 1 omega 1 phi caret lambda is pi kappa gamma plus 1 phi caret lambda, right? Sorry. So I go from gamma plus 1 to omega 1 and then from kappa to gamma plus 1. So I should start from kappa. This should be kappa, right? You go from gamma plus 1 to omega 1, and before that you went from kappa to gamma plus 1. So you really go from kappa to omega 1. But we know that x satisfies these, right? So since x satisfies pi kappa gamma plus 1 phi up to lambda, right? X has to satisfy the full stretch. X satisfies pi kappa omega 1 phi up to lambda, which means X actually satisfies pi kappa omega 1 phi. Okay, so I always forget to do this. And this X has to be in H2. But you can do that, right? It's just a real, so you can put it into the countable whole you were taking. Okay, so X satisfies this. And now we just use absoluteness. So let's see. So I have X satisfies pi kappa omega 1 phi. This is if and only if H omega 2 thinks that's true. X satisfies pi kappa omega 1 phi. Sorry, I forgot these junctions. These junctions all over. H omega 2. But now use elemental the embedding, right? So since sigma restricted to m kappa is pi kappa omega 1, right? I'm going to translate this to H. H satisfies X. X sigma X is X, right? Satisfies this junction. Okay, that changes to phi. But that's contradiction. This is contradiction. Because we were assuming specifically that X does not satisfy this, right? Remember, X satisfies the longer disjunction, but it doesn't satisfy the shorter one, right there. So this is a contradiction. Okay. Any questions?
If you think of an extender as an embedding already from some H kappa plus, I know you don't want, but can you get...
You're just assuming it, Boban. I don't mind at all.
Sorry. No, but let me just say, so instead of having a disjunction, I mean, the disjunction is itself a formula. I mean, you can take the disjunction, it's a formula. Right. So could you simplify it by saying there is a formula which is in H kappa plus, such that, and then there is the image of that by the embedding, which is the extender. You call it P sub E. So X doesn't satisfies the formula and doesn't satisfy its image. So X or doesn't satisfy the equivalence between phi and PE of phi. Is it enough? Or it really has to be a disjunction of?
I mean, then you would get into the issue would be, you know, the kind of iterations you use will be a problem. Are you using the iteration rules? This disjunction business, let's see, where did we, the disjunction business came up in the chain condition, right? Because we wanted to prove that you have delta chain condition. And so the take the long anti-chain, and then we were taking this, so we proved that if some kappa was A reflecting, then it would have to satisfy disjunction of the first kappa many elements of A. It shows up there. If A is anti-chain of size delta, it shows up in the proof of delta CC can say A is phi alpha less than delta, and kappa is A reflecting, right? Then we wanted to show that phi alpha less than kappa is true. And that's how we ended up in this with disjunctions.
I know how that we ended up like that, but I think it would be easier to say, but I don't know, it may be too much to say that X satisfies the formula phi if and only if X satisfies pi E of phi. So that the extender, but
what does it mean to say it's the so
maybe it's
an anti-chain? No, but what would be an anti-chain now? I don't
know. But this would include your case because you have a disjunction and take the disjunction. It's a formula.
This would be my formula, yeah.
What is its image? It's what you wrote. So what I'm saying is more general, but maybe it's too much.
Oh, then my worry would be the this iteration rules. I mean, you know, when you think of extender as embedding, here the length is important. The length is shorter than the critical point, than the image of the critical point.
So it is important that it goes only up to the length, that it doesn't go beyond the. I mean,
it's important because it depends what. I mean, there's Jensen rules, and I think it should be okay if you change the ruls. Let's see. So
of the iteration, how you build the iteration tree, yeah.
Yeah. We're using this. The iteration tree I defined uses what's called Mitchell-Steele rules, where it's the length of the strength of the extender that's important. So you go back to the least model where that computes the power set of the critical point correctly. If you don't, so we, you know, it could be like, for example, I have this picture, then it could be that I use an extender with critical point here, which is between the two. Lambda was my length, was the strength of the extender.
I see, yes.
Which we were also calling length. In Jensen indexing, in Jensen type of things, the length is actually the image. This is actually the successor of this is the length. And then you don't want to allow this. But you could probably still prove something like that. I mean, there is, I think it works out. I think it works out because you could still, you want to stretch it all the way up here.
Yes,
you don't want to stretch
right.
I don't know if, you know, it's hard to iterate with Jensen rules V, the abstract structure like V is hard to iterate with Jensen rules.
And what does Jensen rules means you should not take further extenders with critical point in this interval that you have, right?
No, if you did, then you would have to come back to V. So, I mean, I don't know if Jensen rules make even sense in for iterating V. If it was a mouse, right? So E would have an index. So we say Jensen mouse. This guy would be the image. Let's see, there are two ordinals that are important. This is the image, pi e kappa, and this is the successor of that.
Mm-hmm.
Is in the outer power, right? Mm-hmm. Is the pi e kappa plus of outer power. Okay, so this is how extenders are indexed in Jensen indexing, and you take the outer power of E by E, so kappa would have to go there, right? Mm-hmm. And then you have lambda E and etc. So this becomes the successor, and your extender stretches into something like this. And now, if you want to use an extender whose critical point is here, you have to come back to this model. Mm-hmm. And in the mouse situation, this causes a drop, because if you're below super strong, what the drop is called is that when you take an outer power of such a thing, it was critical point. So say we had actual strength, like eta was the strength. Mm-hmm. If you take if your extender has critical point less than eta, then you, in Mitchell-Steele rules, you still come back to this model. But if it's above eta, then you take the outer power of this one instead of going back. But here in Jensen rules, you have to come back, and this mouse, this one, and it projects to eta. Basically, there's no cardinals between eta and lambda E. So in Jensen, nice, no cardinals between eta and lambda E. Unless you have actual super strong, right? Super strong would mean that eta is pi e kappa. But you can still do genericity iterations. I mean, John wrote up this book that he has, and he did Jensen style iterations for the extender algebra. You have to change the iteration. I don't exactly remember how you do it.
What? Which book is that?
The normalizing and
the what?
Let me. No, I don't normalizing iterations or something. It has a long time.
You mean John Steele wrote?
Yes.
Okay. Well, yes, I think he has two books.
No, I mean, right, like normalizing iteration trees and comparing iteration strategies. The problem with Jensen indexing with this iteration is to show that at the end you actually have an embedding, because if you drop, you may not have an embedding when you actually made your real generic. In chapter 2.6, it's called Jensen normal genericity iterations.
Is it Mitchell-Steele or Steele only? Fine structure and iteration trees.
No, it's a new book.
Oh, okay.
I send you the. A lot of things are easier with Jensen things, and a lot of things are harder with Jensen indexing. So I send it, put it in the chat. It's.
Oh, okay. Normalizing it.
Mm-hmm.
Okay, can I ask another question?
Yeah.
And Niemann has a genericity iteration as well, which is different from this, right? So it's an iteration of length omega.
Mm-hmm.
Can you tell us what it is about?
Well, we were gonna do in the seminar later, but
Okay, never mind.
let's see. I mean, you make it's a. I don't know if I can lecture on the top of my head. It's something like, there is that game you play. If you look at Martin Steele proof of projective determinacy, they translate the game you're playing on, the way they prove determinacy is you have your set of reals and you associate a game to that, sort of an auxiliary game. It's like, think of the proof of pi1 determinacy from Martin's proof, right? So there's an auxiliary game where you play ordinals through this tree and you have measures on the tree. Okay, so they devise a game which produces an iteration tree on V, an auxiliary game. So Itai really got into details of this game, and then he devised one particular. There's some kind of general game that you can play on this sort of. I mean, what does he do? He has some kind of continuous map from reals to iterations on the countable thing. We'll do this. I mean, okay, let me just tell you vaguely what this is about. They have some M, which is, and delta is wooden M. Right? So now you have a continuous map X going into Tx. So continuous map, it means that it's built from finite ones, right? So basically a system. So you have a system, S is a finite sequence of integers, and Ts is a finite iteration of M. And if S extends T, then Ts is an initial segment of Tt, right? And it's very similar to just trying to do Martin Steele proof, which is similar to trying to do the Martin's proof of determinacy. So you build these trees, and then what he showed is that any branch you pick, any well-founded branch, right? So now you have X goes to Tx, which is the union of Ts. S is an initial segment of X. Then any branch you pick, any well-founded branch Tx makes X generic. Or the collapse. And if you just do what he did, which is sort of one of the, well, if you understand the proof of Martin Steele, then what Itai did is sort of natural next step, and then this comes out of it. It's much more complicated than Wooden's one. The nice thing about this one is that delta is fixed. So in Niemann case, you have M to N via T such that one length of T is omega, two J of delta is delta, meaning the Wooden is fixed, which is used in some applications. What else is and of course, the most nicest thing is that we know how to prove this form of irritability. Yeah. So while Wooden's genericity needs omega 1 plus 1 irritability, which we don't know how to prove. We don't know how to prove in general. Niemann's still needs omega plus 1 ergodibility, which is true. So this is the most important difference. And so for proofs of determinacy, which is why he needed this version, all you need is this version, yeah. But I don't think right now I can tell you exactly what this game should be. It's some way of converting really the ranking, yeah. And you have a tree, homogeneous tree. You could show that there is that the complement of the tree. You have, let's see, the steps go as follows. We have a T. We have T that is homogeneous. So that means T is a tree, yeah? Descriptive set theoretic tree. T on omega cross kappa. So homogeneous means you have a system of measures such that Ts has measure 1 and X is in the projection of T if and only if the sequence is well founded. Oh, and you need that mu T projects to mu S for, right? So it's just sequence.
You mean the ultra power of the is well founded? When you say
yeah.
the sequence is well founded.
Yes. The sequence is well founded if because of this projection you have an embedding from, you have. Okay, so let's see. So we have. You can let the mxn be the ultra power of v by mu x restricted to n, and so we have embeddings from mx. You have embeddings pi st whenever s is an initial segment of t, right? And then this just means that the direct limit along x is well founded.
Yes. Okay.
It's kind of like iteration tree, but you have these measures. Okay, so now you can build a tree on the complement of the projection, right? So that a complement is the projection T complement. So you can try to mimic Schoenfeld's construction. And how you do that? Well, you basically want to prove that the direct limit is ill-founded, right? So you put finite sequence and H, which is going to be sequence of ordinals, right? So this is in omega less than omega cross maybe some other kappa, because it will not be a tree on kappa. Like the Schoenfeld tree is, the tree for sigma 1 is on omega, Schoenfeld tree is on omega 1. So this will be tree on some bigger lambda. So you'll put this in your tree if and only if. So you want to say that pi s restricted to I, s restricted to I plus 1 of h. Let's see, so how does this make s? Is the I guess the I is bigger than h I plus 1. Right, so you have MSI and you have MS restricted to I and you have MS restricted to I plus 1. So you're saying that your HI is recording some ordinal here and HI plus 1 is recording an ordinal below the image. And of course, if you had a branch, it would be ill-founded because this one would be mapped above HI plus 2, right? And then the direct limit will be ill-founded. So the upshot is that if some real gets into the projection of S, then it's no longer in the projection of T, so it's in the A complement. Then, okay, so now you want to prove projective determinacy, yeah? So want to prove projective PD, right? So start with, so Martin did what? Martin did Pi11 is Holmes's name. So this gives you T on omega cross omega 1, that is homogeneous. Assuming measurables, right? And then you do, so now let S be the tree that we've just built. Be the Morgan Soloway, which is the one that I just described, tree for T, right? So you have these homogeneous measures, you continuously prove that it is ill-founded, the direct limit is ill-founded, that gives you a tree. Okay, if you want to prove now Pi12 determinacy, if we want to prove Pi12 determinacy, we need to prove that S is homogeneously system. We need to prove that S is homogeneous. And then if you prove S is homogeneous Disuslin, then you just do Martin's proof for Pi11 determinacy, and that tells you Pi12. Yeah, that just works. And that's what Martin and Steele did. They ended up finding an iteration tree on V, which was equivalent to having these measures around, basically. Which you know, I don't remember exactly on the top of my head how you do this. I need to review. This is as much as I can say at the moment. How much time do we have?
Well, we spent the whole seminar before, I mean, discussing what we did last time. That's fine.
Yeah. Do you want me to tell you the proof of that you can have length omega 1 iteration with no branch?
Yes. Well, I won't. But no.
Yeah, because we have some time, and this is, I think, interesting. So okay, so now we have, in a few seminars back, we actually had a wooden. We had a model with a wooden kernel which was errable, right? So suppose M, so this equals L of V delta M, V delta countable, and M thinks delta is wooden. Okay, we also had that it's fully errable, and suppose M is fully errable, which we had if, for example, V is closed on the sharps and there is a wooden. Then we have such a thing. Okay, fully errable means any length. So this implies that zero sharp, every real has a sharp. I mean, A, B together, right? So A plus B implies every real has a sharp. What I meant in this parenthesis is that if you want to get AB, you could assume this and that would give you AB. Okay, but that's not the interesting part. The interesting part is to assume AB, and that gives you every real has a sharp. The proof is just a genericity iteration. So suppose, so let's prove that. right? Proof. Suppose X is a real, so X codes V delta. Now in L of X, we try to iterate V delta M. We try to iterate M to make X generic. Let me and eta is the least such, yeah, and delta is least eta such that L of V eta M thinks eta is wooden. So we had exactly this, right? If we assume this hypothesis that V is closed under sharps and there is a wooden, then we took the least delta which survived wooden, which stays wooden after adding ordinals, then we proved that it's erasable. Okay, so we try to iterate M to make X generic, but let's try to violate covering. So for example, let's do not X generic, but well, okay, we can make X generic. So how? So first, iterate M Aleph omega +1 times via its least measurable. So let N be with this. This is red, right? So we just take the least measure of M and hit it Aleph omega +1 times. Now L of X thinks that cardinality of N. I mean, by writing things like this, I just mean that the important part of N, right, is Aleph omega of V. And okay, so now we iterate N to make X generic. What can we show? We can show that the iteration. Let's see. So the iteration cannot stop before stage Aleph omega plus of L of X. Why? Right. So suppose you did that and the iteration did stop before reaching the successor of Aleph omega. Right. So assume otherwise. And let J and K be less than Aleph omega plus L of X iteration in L of X such that X is generic over the extender algebra of K at the wooden of K. Right? So K has a wooden J delta. Let's, well, I already did the first iteration, so let eta be the wooden of N, and this should be J eta. The delta was the wooden of M, so we first went to N, now we went to K. Now we made X generic. But what do we know about the extended algebra is CC, yeah? The J of eta CC. So K X thinks that J of eta is a cardinal. But because the length is less than Aleph omega plus, right? So this is one thing, and the other thing is J of eta is less than Aleph omega plus of L of x, because the length of the iteration is less than that. But obviously it's bigger than J eta. That was the point of iterating the least measure Aleph omega plus 1 times, so that it would be, the wooden would be above. Okay, so we created a cardinal between Aleph omega and Aleph omega plus, right? This is contradiction because that J of eta is a cardinal of L of x, right? It's a cardinal of K of x, which is bigger than L of x, and which contains L of x. And it's a cardinal, so contradiction. So the iteration has to go up to Aleph omega plus many stages, right? So the iteration lasts Aleph omega plus many of L of x, many steps. Now let T be the resulting iteration and B be the branch. Now B cannot be inside L of x. Now T, I mean, it takes some argument to show this, but can show that T is inside L of x. Meaning this iteration we could just do it inside L of x. But B is not going to be in L of x. Why? Because pi, you could show that pi T B eta, which is the wooden of n, is equal to that. And it's continuous at eta. Remember, there are no measures at delta, at eta. So the iteration embedding is always continuous at non-measurable points, not non-measurable inaccessible cardinals. And so you have continuity and you have that it's going to Aleph omega plus. So the branch couldn't be inside L of x, because otherwise Aleph omega plus would be singular, right? If you take these two together, you conclude that if these two, because of these two, if the branch is in L of x, then they together imply that cofinality of Aleph omega plus of L of x as computed inside L of x, if the branch was in L of x, is omega. So this is you could have just done this for omega at the countable level, and you'll have a tree of omega length omega 1 whose branch doesn't exist. Okay, but now you have the sharp, because the branch is outside and it singularizes, right? Now, by the same reasoning, well, I mean, this is just a side comment, right? If branch was in L of x, then you'll have cofinalities omega. But if the range is not in L of x, then these two together imply cofinalities omega anyway, right? So we have the cofinality of Aleph omega plus of L of x is omega, but that's while it's covering. So covering first. If you did the same proof, I mean, it's the argument for length omega 1 iteration without a branch is exactly this, right? So if we just iterate m to make x generic in L of x, then we will have T, who's of length omega 1 of L of x, but no branch of T. Because any such branch singularizes omega 1. Right. It takes some explaining to do why you can actually do this iteration. I mean, there's something to think about, right? At limit stages, we have to pick a branch. Now, I only said that X codes M. I didn't say it's also coding the strategy. So L of X a priori does not know the strategy of M. And so how is it going to pick how can you pick the exact same branches that the strategy is picking at some countable limit ordinal? And the reason goes back to the proof of irritability we did. It's because that branch is sort of, you can guess what that branch is, all the countable levels. And so how you know that it's going to go omega 1 stages, that's this proof. And that's this proof about getting a cardinal between this proof. No. I did that proof, I just cannot find it. Well, you know, you have to argue at the end that you cannot stop this generous iteration at the countable stage. If you stopped at the countable stage, your wooden would be countable inside L of X. But because of this delta CC, when you add the real, it remains a cardinal. So that means omega 1 of L of X is countable inside L of X, which cannot be. So once you prove that you can guess the correct branches for the countable portions of the tree, the iteration has to last omega 1 steps, but then you cannot find the branch. Yeah. So this is how you prove.
Where is this written up?
When we get off, I think it might be in this paper that John wrote. I think this is such a standard thing in model theory. I think maybe nobody ever bothered to write, but I think John ended up doing it in this paper. I think the paper is called "How is a core model?" It's in one of these Cabal volumes. Unfortunately, it's not on his website.
We have the Cabal volume, so we can check.
It's in the last one.
You mean the new edition, or?
Yeah, new edition, the last one.
Cabal. So that is number 4, right? Large cardinals determinants in other topics. That must be it. Soloway wooden Kekris steel on Watt's conjecture. It's not this. No.
No. Hard as a core model. Yeah, it's there.
That's not okay. Or maybe this is the next one.
Oh, maybe it's the third one. Maybe I'm wrong. Maybe it is the third one.
Okay, let me try the third one. Hod and its local versions.
Hard as a core model.
Hod is a core model. Is that it?
Yeah.
Steel and wooden. Hod
Yes.
is the core model. Okay. So I put it in the chat.
Should be in there.
Here? Oh yeah.
I'm just trying to see if it is in there. Well, we need to go to the other one. How about I'll try to see where it's written up and I will send you.
I put it in the chat.
Okay.
Yeah, it's in the chat. Oh, the whole volume. Okay, very good. I
Oh,
won't
you
tell
did the
anybody.
entire volume. Wow.
We won't go into the details.
Look at theorem 3.16 of that. There's something called pseudo-genericity iteration. It's similar.
Okay, let P be a
3.16.
suitable M1 like.
Yeah.
Z be a real, then it.
Yeah, but I don't think he's explaining. He's kind of writing it for experts. He's not really explaining why you have the branch, and maybe
It's
he's
very short, right?
oh, has to be somewhere. Maybe it's in the. I can do this more carefully next time. It's on page. Well, I don't have the book version, but on page 10 of the paper version, there is this lemma which you use 3.10. Okay, I will do this more clearly next time, more carefully next time.
Okay.
Okay, so let's go to the other one. All right, guys, see you.
Bye bye.
Okay, thank you.
Bye.